great pleasure to start off the inaugural Stephen Malkin Lectureship. Steve inspired others to do their very best professionally by the example he set, not by directives or dictums. He generated love and goodwill in everyone with whom he came in contact by asking a very simple, but too often unasked question, how are things going? And he was an engineer of extraordinary accomplishments, a member of the National Academy of Engineering, and a bright star wherever he went. Steve's wife, Maccabee, and his daughter Ruth are in the audience, and they know I could go on and on and on about what a wonderful person and colleague was Steve. I also want to take a brief moment to acknowledge the generous sponsors of the Stephen Malkin Lectureship. They include Joseph and Martin Goldstein, Senka Bain, leaders in advanced abrasive technologies, and many other staff, faculty, and alumni. Many of Steve's graduate students are now top-level executives at Senka Bain today, and I hope you, the faculty, and others have time to speak with them at the forum after the seminar. I could thank many more, but I want to end by personally thanking Fritz Klocke, a longtime friend and colleague of Steve's, who has traveled all the way from Germany to speak with us today. Dr. Klocke is the chair of the RWTH Aachen Laboratory of Machine Tools and Production Engineering, as well as head of the Fraunhofer Institute of Production Engineering. His various awards and accomplishments would easily fill an entire book. I will mention only one. The Society of Manufacturing Engineers awarded him the prestigious Eli Whitney Productivity Award for the development of a number of new production processes and his findings in further development of existing production processes. Every year, the SME awards 7 international awards such as this to individuals in production engineering who have rendered outstanding services to production technologies and processes as authors of scientific and technical works in training and teaching, as well as research, management, and the service sector. Dr. Klocke richly deserves this award. At this point, could we please give a big welcome to our speaker, Dr. Fritz Klocke.
Yeah, good morning, everybody. In particular, a very warm welcome to the Malkin family, to Maccabee and to his daughter. I'm really impressed seeing so many people coming here this morning to participate in this lecture. So I'm really deeply impressed. Before I go to the talk, let me say a few personal words. I really do have deepest respect for the work and for the life commitment of Steve Malkin. So I got him to know in 1982. So that was in a time when I first visited Haifa, the Technikon. Steve was there, many other professors were there. I remember Professor Weil was there, Professor Baer was there, Professor Lenz was there, so the whole family was there. And many other people, also Steph Wertheimer was there. That was the first time when I came into touch to Steve, and he really very warm welcomed me, and he took me around and he showed me his test equipment in his laboratories. So that was a time in the 80s where in Worcester there was a counterpart of Steve. In Worcester there was a Hield company. Hield was a subsidiary of Cincinnati at those times, and they did make internal grinders. So in Hield there were 2 other guys, that was Lindsay and Hahn. And so what I learned from those days was there are 3 people in the grinding world. So if you go for grinding, look at these papers. That was Steve Malkin, that was Lindsay, and that was Hahn. So that was my first, my first appointment with Steve Malkin. So in some ways, I have got to learn Steve to be very unsophisticated as a person. But when it came to the science and engineering, he was extremely sophisticated. So, and he talked a lot of energy partition of heat generation and heat flows into the workpiece, etc. So that's what we really learned from him. So then I went to industry in '84. I was for 10 years with Winter Company, which is taken over now by Saint-Gobain. So I worked in Hamburg for 10 years. I was the CTO for Diamond and CBN Tools. And in 95, then I returned to Aachen and went to the university. So at those times, if I look back in the 80s, it was a time, it was really a thrilling time and enthusiastic time, because in 1957, the man-made diamond was invented by General Electric in Schenectady. And 10 years later, then in 68, it was the CBN. So the lifespan of super abrasives came. And Winter in Hamburg did have the exclusive rights to bring these new abrasives on the marketplace in Europe. So we really did have very close relation to the GE people in Schenectady, and we really learned from scratch what diamond and CBN could do. So that was wonderful. In 95, when I then came to Aachen, I became also a member of the International Academy for Production Engineering, CIRP. Steve was already there. So he was not just one who made good contributions, he was always there. So that's what I learned. He was always also there to raise his hands and to take jobs back home, and to do something for the community. So on the one hand, his advice was sought after by many, many people, because he knew so many things about the grinding and the engineering. But when it came to the point that there was commitment to be taken, also to do something at home, to take homework back home, he was there. So that's what I also learned from him. And sometimes he took me aside and he said, okay, Fritz, I tell you one thing. First, learn about the basics and the physics behind. And if you have understood what is really going on, then make practical applications and turn your knowledge into practical applications. So in that sense, I would also consider Steve to be a real engineer. So engineering or engineers, if they do research, they always have to solve a practical problem. It's not just curiosity driven, it's also driven from the praxis. But not too fast just to fiddle around with parameters and make it better. First understand what is really going on, and then have a general basis, a general platform, and then bring that knowledge to industry. Also in that sense, he was a brilliant engineer. Therefore, as some more, it's really my pleasure, and it is really an honor to be here and to give this talk in memory of Professor Steve Malkin. I come from Aachen, as mentioned. We have in Aachen the Laboratory for Machine Tools and the Institute for Production Technology, IPT. So we have on our payroll about 600 full-time employed people which do research in production engineering. And out of the 600, it is 350, 360 research engineers. And we have 20 people working in Boston. So that is, these are our laboratories. If we say we are 4 professors, board of directors, and we have a total budget of 60 million per year. So we have to see that we really get that money in-house to really also able to pay the salary of our people. 20% comes from the state as a base funding. So base funding is free money. So we take that money for education, for example, also for some maintenance, but even more important, that is free money for us. We can decide on our internal research projects. If we say we would go for that, whatever it is, then we take this money and we do some research in before. And as we see there's something in there, then we can go to industry. It's a sort of seed money. We go to industry and then we sell the idea. And we have industrial projects and public projects. So that is our environment. So what do we do? Okay, of course we do research, we do education, and we do service. And that brings me to today's topic. So modeling of grinding technology, so that is something about the fundamentals, about the basics. Gear grinding is really a practical issue. So now I have this combination, what Steve also so liked, to say, okay, learn about the knowledge, learn about the basics, but then solve a real problem. And gear grinding is one of the most complicated and most delicate grinding processes that we have. So why gears? Is gears old-fashioned? If you go to the marketplace, if you ask normal people about gears, they most likely say, okay, that is blue-collar work and that is steam engine. But we have gears in many, many different applications. So that is just high precision gears, as you see here. Then we have, of course, the cars and the trucks. So by the way, we make per year about 1 billion gears, pairs of gears, 1 billion. And that is increasing. So we are making a lot of gears. And if you were a designer in a car company, and if you have to lay out a gearbox, you would say, okay, I shoot for a lifetime of a normal gearbox for 200,000 kilometers, 250,000, 250,000 kilometers. If it was a truck, you would calculate roughly about 1 million kilometers lifetime of a gearbox. So if you run into trouble with your car, then if you are far away from 200,000, you might ask for warranty. But if you are above 200,000 kilometers, then most likely they say, okay, that's normal life. We have also gears in planes. That's what people sometimes really don't consider. Also over the years, there are little gears in planes which just adjust the flaps or other components. But in September of last year, a new plane was launched by Airbus. And this plane has a planetary gearbox right after the fan. So that is because if the rotor runs very, very fast, high speed, you need this gearbox to really bring the rotation of the fan down. Otherwise, you would exceed sound speed on the tips of the fan. So now we have also these gears in a real airplane. That is a Pratt & Whitney turbofan. And that is increasing. So that was just an eye catcher. So these are the flights per day. So we have per day about 200,000, 250,000 airplanes on air, airborne. So every airplane, in average, 2 engines. So 400,000, 500,000 engines on air every day. That is also well known. So that's energy. So if you see these windmills, you might distinguish into 2 classes. So one is where the wind power is directly converted into electrical energy, so 50%, and the other 50% has a gearbox generator and the windmill. And the last one, of course, we have really big gearboxes, for big ships or for rock crushers, etc. Rock crushers, just to give you a number, rock crushing, you might have 1 million Newton meters torque. Very low speed, 1 million Newton meters torque. That is really a big gearbox and big gears. So now the question comes up, how is the gear made? So that is dependent, of course, also on the size of the gear. And I take now the gears which are used in trucks, which are used in automobile, in personal cars. You start with a blank. You cut off the teeth, and after that, you normally have a heat treatment, so case hardening, and then you do hard finishing. And that brings me to today's manufacturing processes I will look after. That is the hard finishing processes, the gear grinding. So why really do we shoot for models in modeling gear making processes? Of course, to find optimal setting parameters, so to keep the costs down. So that is number one. But what is even more important, to predict lifetime of a gear. So any cutting process which you have, you need energy, and at least a portion of this energy goes into the material, goes into the component, and it changes the properties of component. Whether or not it's that is allowed within the tolerances or not, that is the second question. The first question is we really have to consider, we put energy on the surface of the material, of the component, and then we change the component properties, and at the end, most likely also life. And we would like really to predict the lifetime. So that's the reason why we have this approach of modeling. And it's always our target also really to come up with a really very sound model which is based on physics, on constitutional parameters, etc. The problem is so many interactions. Another problem, boundary conditions. In Germany, which we sometimes do not know, then we have a set of parameters and a set of very nice differential equations, but as we don't know the boundary condition, then also our result is not good enough. So in German, we have a saying, it says, God made the differential equations. The boundary conditions were made by the devil. And that tells the whole story. So then we go the next step. So we have simple models. We use the computers, what is good. But also heuristics. So if you have experienced people that really know what they are talking about, it's also very, very valuable. Ask people. So heuristic and rule-based model is also good. And the last one, and that should be also the last portion and the last topic of my talk today, is sensors. Why not to combine models that we have with the real world, where we really hear, smell, where we look into processes, where we put sensors on, and then combine a good modeling with the real life, which we can take from real processes. So then we have the virtual production, of course. That's what we look at, to do everything on the computer. And it's not just one process, it's a whole process chain. Start with a blank and end up with a component. And we have the real production then, where we have sensors, where we have our controllers, which also be a lot of good information, and really match that together to get a better insight of the process. So let me come back to the gears. What is the beauty of the gears and of gear making? First, we always start, we just analyze contact conditions. So we forget everything. So we forget the grains. We just have a wheel, and we have the gear, and then we just analyze how the wheel penetrates through the workpiece. And we can already learn a lot of things when we just do that. So that is a geometrical analysis or kinematic analysis. 3 processes here. I will focus on the profile grinding and on the generating grinding. I will look a little bit at the honing, what is also in fact a grinding process at low speed. So more or less, if you look at this slide, they look more or less the same. Okay? So profile grinding should be the easiest one. So that's what you most likely consider, because in profile grinding you have a wheel, and that has the reverse profile of the tools to be ground. So you copy just the wheel into the workpiece. So that's easy. Oh, okay. As we go a little bit more in detail, we see it's not so easy. So many different contact conditions over the profile length. And if something really is different, you also have different conditions of the flank of your part. So that's what you first really have to analyze. What are the conditions, the engagement conditions over the flank? Obviously, a lot of things to be taken into consideration, and that's what you already can learn just from the geometry. It's good. So let us go to the generating grind. So in this process, that's very often applied in industry. So you have this profiled gears. They can be electroplated, CBN for example. They can be conventional, so then they are going to be dressed. So, okay. But then you do one gap and you index further, step by step. So question now was, could we also come up with a process where we can get rid of this indexing, because indexing is always something that goes along with accuracy. It goes also along with time. So why not to have a process to make these gears in a continuous way without any indexing? Can that also be considered? As we are talking involute gears, so that was one of the assumptions which I didn't touch, and there's many good reasons to make an involute. I have this little animation just to remind you how an involute is going to be made. You have a base circle, you have a straight line, and as a straight line rolls off a base circle, you get an involute. So that's how it looks like. So easy thing. So what you need obviously is you need a base circle, rotation, easy to be done in a machine, and you need a straight line which rolls off. Okay, straight is always good. So if it is profiled, it's more complicated. Straight is easy. So now you could, and engineers did it 100 years ago, and one of these pioneers, they sit in Rochester, New York. That's Gleason Company, Fauter Gleason Company. They came up with this idea to make a continuous process where you really have a combination and a coupling between rotation and translation in a very distinct way. And at the bottom line, what you get is an involute. That's exactly the profile you like to get on your gear. Okay, so We look at it. Obviously, they work very nicely to one another. That's what we see from this little animation. What we see is all the pitch points, they sit on one line. That's also good for some other reasons. So obviously, it works. How to make it? Now we go a little bit more into detail. We have our tube, we have our workpiece, and what we now see here in this slide, we have different contact conditions. There is not just one flank in contact. There might be 3 flanks, 4 flanks, 2 flanks, whatever. So variation in contact condition. Also the points of contacts do vary. And if that is the case, so the forces do not compensate. You have resultant forces, and resultant forces can run you into trouble because of deflections, etc. So what is the learning? What is the message? Just by doing this geometric analytics, you already see, take care. Look at it. And if you change now the kinematics, and if you change diameters, etc., you also change these conditions. What is already good? And that can easily be done on a computer. So without any knowledge on grinding. It is just geometry. Okay, so that is a real machine, how it looks like. Yeah, okay. So that is a real gear from a windmill, from this planetary gears from a windmill. That is our grinding worm. You might see, or at least imagine, that are straight flanks, so that's easy. And they very nicely work together with the gear, and it's continuous. So there was no need to index them. So that now we have another process. So we have profile grinding, we have generating grinding. And that is the third one we can look at. So I picked this, what we call honing or slow motion grinding. We could follow just one particular point, how it travels, the trajectory, how it travels over the flank. And then we see the trajectories. And that is a particular pattern what we see here. And it comes out of this process. We see they are banded convex or they are banded concave. And there is in the middle the position of the pitch circle, everything is 0. Why is that important? In a gearbox, you have 2 gears. They work together with one another, and you have lubrication in between, and you have tribology. And if you now have these structures, these microstructures, they could be really helpful in bringing and feeding in oil, for example, and make your gearbox working more efficient. And that's what you really also see on the flank. Also, something independent on the grids you use, independent on the wheel you use. That's what you just can learn from kinematics. Okay, so that was done now. We know the contact conditions, macro scale. We go a little bit deeper in the process. We look at the grinding wheel. So all the grinders here from Saint-Gobain, they know that. But might be some others which see some surprise here. So you have the grinding wheel, and the grinding wheel is easily composed. It's composed of grids, it has pores, it has bonding material. Okay? The grids provide the cutting edges. So what you see here from the cutting edges is they are geometrically undefined. It's not a sharp cutting edge. It could be sharp, but sometimes they are also just rounded. That's number one. And if you just count the grids, that doesn't give you the number of cutting edges. There might be one grid which has more than one cutting edge. So the number of cutting edges differs from the number of grids. Okay, second thing. The third what you see here is not necessarily all cutting edges which you see under the microscope come into contact with the workpiece. They are hidden. They sit a little bit deeper. So there is a space. And they are randomly distributed in that space. And depending on your kinematics, depending on your infeed, you have more or you have less cutting edges. Okay? Not bad to know that can happen. The second, now we look at the cutting edge. Cutting edge can become dull, can break. The whole grain might disappear. So there's also fluctuation in the number of cutting edges. So that has to be taken into consideration if we are talking about how a grinding wheel behaves over lifetime. Everything goes into the topic heat partition, goes into the topic energy conversion, goes into the topic energy impact on the flank of your ground gear. Okay, so more or less you're happy, now you know everything, you run your process, and what you see is marks. So, well, that heat and grinding, that goes together like twins. You always have to fight the heat, and the heat impact on the surface, in particular hardened steels and gears. So you see marks. Is it a bad thing? At least it indicates there was a change. So, and that's what grinding people call, these are burning marks, and burning is something really very, very bad. I tell you one thing, when I came to Aachen in 1959, in 1998, a German company delivered windmills to California, to an energy provider, 6,000 windmills, and they were placed on the hills around the sea over there. And then I got an emergency call from these guys. They said me, Fritz, we really do have trouble in California because one after the other of our windmills, they break, they fail. We don't know why, but the customer is really punishing us. They have 6,000 windmills, and now every day 20 windmills fail, and we do not know why. And I asked him, okay, well, how can I help you? I'm not a windmill maker. You are the guys, yeah? You make windmills. I say, well, do me a big favor. I would like to have you accompanying us to see the key account in California. If we come with somebody from the university, they might be calm and say, okay, they do anything, and they bring really expert people. And that's what I also really knew from my practical work. I was also punished by customers. Sometimes really you have problems, and the only thing what you can do is, if a customer has problems, go there, ask him, can I help you? So, okay, so that was, at the bottom line, what was it? It was grinding burn. So in the making of these gears, there was heat accumulation, and that wasn't seen, so they really didn't look for the grinding burn, and there was a heat affected zone, and at the bottom line, the teeth broke. So that was the simple analysis. So today they have sensors and they have quality inspection at the point. So what happens now with the heat? So the heat goes into the workpiece, and the heat changes the structure. And so what you might see is really, if you do a cut and if you put it under the microscope, you really might see these white zones, as the people say, because they appear white. Then if you ask people from the material science, they say, okay, we look even more into detail, higher magnification, they say, okay, completely different structure. So ultra fine grained, extremely brittle, etc., etc. And now you see that you really have to prevent this sort of inadmissible heat influence. So if you don't, then this happens, yeah, damages, etc. So bottom line at this point in time, modeling is good, modeling is important, and even more emphasis is put on modeling processes. And at this point in time, I do have two pieces of information, a good news and a bad news. Starting with the bad news, all models are wrong. That's the reason, it's models. Okay.
Keep us in business first. That's
absolutely, that is good. The good news is some are useful. That is not from me, that is from this guy. He was a mathematician, he lived many years here also. He was born in England and he lived there in America and did mathematics on statistics. But I think that is really a wise saying. That's what we always have to consider. Some are useful. And engineers are always shooting at the useful ones, okay? And they know a model is a model. Okay, so now, having said that so far, next step could be combine model with sensors. So with real insight information from the processes, and then make your model and your prediction even better. Let me go to the calculation of cutting force components in grinding, what is really a very delicate thing. Okay, so that is a formula. Steve also used that very, very often, and this formula was at the end was investigated at MIT in the 70s from a German researcher. He worked at MIT and he came up with this model. It was Günther Werner, by the way. He said, okay, you have seen, so we have so many different cutting points, cutting edges, and they go deeper and less deep into the workpiece material. But one distinct value could be the maximum ship thickness, theoretical, not practice, theoretical ship thickness. And he came up with this formula. And the good thing, the beauty of the thing is, it really gives you the influence of the grinding tool, that is yellow, because that is the number of cutting edges that you have. And that comes from the concentration. If you have a wheel with 24% volume of grains, you could calculate theoretically number of cutting edges. So that's what we call cutting edges static. So you can count them. So that is in the wheel, comes from the recipe. And then they have your red ones. The red ones comes from the machine. These are the setting parameters. If you go faster, if you go slower, has an influence on the ship thickness. Also the infeed has an influence on the ship thickness. And the last one, that is this geometrical value, which really considers the curvature of the wheel and the workpiece. So not bad. So if you know this, at least you can do qualitatively comparisons. You say, okay, I have a reference point, and now you could discuss what happens if I double wheel speed. What happens if I double infeed? So what happens? So in which direction can I consider that the ship thickness is going to move? Okay? And then knowing that, you could say, okay, if that was the case, I could also at least predict somewhat cutting force components. I also could predict surface roughness. I also could say, okay, heat partition might be also a good measure. Material properties, okay, might be too far away. Second, okay, that was just one value, but the theoretical chip is a volume thing. It is not just one length parameter. So you have to consider some sort of volume. And what you see here is, so that is the theoretical volumetric chip. So that gives you even more information. If you know that, you even have even more a clue what really happens on a single cutting edge. For the moment, what I'm talking about is everything is, again, geometry. It is kinematics, it is geometry. I didn't touch mechanics. I didn't touch ship formation. I'm just talking about the constitution parameters of a wheel, of a workpiece, etc. And I get some information what could happen theoretically. So that was brought in a huge program. And well, now we can run on this base, we can run all these processes on a computer, and we can do parameter studies. Yeah, you see reference values, and we change parameters, and then we see, okay, if we do this one, and this one, and this one, we could expect the process behaves this way. Real values now would be even better. Okay, for the cutting edges. Okay, so then we take a real grinding wheel, we put it under a microscope or on any other measuring device, and then we measure the topography. So now we really get micro information or information on the micro scale from the topography. Now we see the grids. And we also have real grid shapes. And you would say, okay, that is just for one wheel, but you have thousands of wheels, 1 million of wheels. That is correct. So what you could do then, make groups and representative topographies out of these groups, and then set up a library. And then you have your topography in a library, and you couple your real geometry topography to your geometric movement, to the kinematics, and then at least you are even closer to reality, because now you have real parameters. Second thing is now, as you also have the kinematic, you could calculate that were the static cutting edges, so that's the cutting edges which you can count. And now the kinematic really reduces this number. We call them kinematic cutting edges. Now you really see how many cutting edges will be engaged, will be in touch to the workpiece, and that gives you even more information what the cutting force components could look like. And again, you do parameter tests on a computer and not on a grinding machine. In any case, you have to verify these tests then, but you do the big bulk of simulation on a computer, and then you pick out distinct conditions and you verify that in real grinding tests. So if that was done, of course, people came and say, okay, grinding wheels, that is also good. That is also a business in itself. So we have grinding wheel maker, and we have machine tool makers, of course, and grinding wheel makers. Let's do the same thing just with a grinding wheel. So if you make a grinding wheel, you start off also with a recipe. So somebody sits at a computer and says, okay, that is the recipe. I take this one and this one and this one. These are the portions. I mix it together. I press it, put it in an oven, fire it, and have my grinding wheel. Sorry, I do it very easy. I know it's a little bit more behind, but these are the main steps, okay? Okay. So now, if that was done, or if that were the main steps, question was, let's model a grinding wheel, the grinding wheel making. Let's also try to do that also on a computer, where we just have to know the bonding material, where we just have to know the grids, grid size, shape, and then also let's do the recipes on a computer to see how a grinding wheel could look like if we do everything on a computer. So on the slide above, what you see, that is a plated wheel. You look at it, what you see randomly distributed. So that's not a pattern. It is just random. The grids are randomly distributed. Number one, number two, you see the bonding. And you see the grid shape. And you might see there's not one distinct diameter of the grids. There's also a spread. If you say grid size is 180 mesh, then it is between 120 and 240. It might be a Gaussian distribution curve, but you have also always a spread. Good. As you know, you could start, okay, let's do the modeling. Same thing again, start with the geometry. The grain shape, put it in an X-ray examination, find the grain shapes, model the grain shapes, and now get a numerical model of grains and put that in your library together with your. So that is a real grinding wheel. It's a resin bonded grinding wheel. You just look at it. You see the grids. You see the bonding, and now we did some measurements to really see the real distribution of these grids. And what we found out was, so we made grinding wheels, same concentration of grids. So the volumetric concentration of grid was exactly the same. It was 24%, C100 or V240, so 24% was the grid concentration. The grid size was also the same. The only thing which was size was the same, geometry. The only thing was different was the bonding. So what we see here now, the slide might be a little bit busy, but if you look carefully, you see these yellow bars, which represent ceramic bonds. And you see the blue bars, which obviously don't fit to 100% to the yellow bars. So there's a shift in between. And the only influence here is the making. It's a grinding process. That was a phenolic bond or an epoxy bond compared to ceramics. And if you process a phenolic bond, okay, you do it heat and pressure at the same time. And then you have high viscosity, and then also the grids start to move, and you also change volume. At the bottom line, you get a wheel, despite the fact that the number of grids were exactly the same. The distance between the distance between the grids is different. So, and if that is the case, you have different grinding behavior. Okay? Okay, so now we need software engineers and we need mathematicians, because if we do all this digitization, we get bunches of points. Yeah, you see one grid, 120 gigabytes. So for the university, no problem, because we have high computing, so we can compute 1 week and then we have 1 point. So, but that's not good for industry. So then we need people. They say, okay, reduce the models. Reduce the models that way that we are getting faster, better algorithms, and we are calculating faster, etc. Okay, so I stop here. So at the bottom line, what we have today is at least the beginning of the modeling of grinding wheels, real grinding wheels, considering wheel shape, considering grid shape and grid concentration, to come up with a topography which we then again can bound to our geometrical model to do the engagement analysis. Heat partition. So I cut it a little bit shorter here. Heat partition, same thing. So just one single grid. So the grid goes through the workpiece. And then as the grid, so first the grid travels through air, and then it touches to the workpiece, first contact, and what you have is elastic deformation, followed by plastic deformation, and then you have a ship. So that is easy. So on this path, we have this energy conversion, yeah, from the rotational energy, from the mechanical energy into heat energy. And then as the heat is there, depending on the contact conditions and on the time durations, the heat travels either in the workpiece, either in the grid, in the bonding material, or it's taken off by the coolant. So we are interested in this QV because that is the heat that goes into the workpiece and which we really have to know in case we like to predict functionality. So did the same thing. Came up with a single grid, looked at the single grid, really studied what happens if a single grid goes into the workpiece. So what is the portion of the elastic energy? What is the portion of the plastic energy? So at which point in time do we reach the damage of the material? So little cracks are induced, and then the first chip is made, and at the end to really learn more about what happens at a single cutting edge, convert that to numerical simulation, and at the end feed everything together and hopefully have a model which tells you what the portion of energy is, partition of energy is, that goes into the workpiece under given conditions. So if that was the case, now you can fiddle around at your computer. You just can change setting parameters to see it's better, it's worse. New grinding wheel, better, worse. So that is the beauty of this toy. You told me yesterday toy. That is really a toy. That is really a toy. Okay, so now, any questions? I'm talking. Are there any questions? Yes, please.
How do you verify the findings of the heat partition?
Indirectly. So we do it. Let me first do this paragraph because the heat partition now goes into the workpiece, it changes the material. And then we look at the material and we see the changes in material. And we correlate that to the heat impact. And then we could verify also our model whether we really did have the same assumptions. Material properties. So the heat now goes into the workpiece, okay? I was talking gears, okay? And so what we really do know is it is not just the heat which affects the structure. It is also the mechanical stress. It's also energy. Energy is energy. So the material cannot distinguish whether it was heat or whether it was mechanical. Material just feels stress in the neck, pain in the neck. Okay, and doesn't care where it comes from. And according to the pain in the neck, material changes properties. So as people do. Okay, so as we now know what the mechanical conditions are, so we know the cutting force components, we also have some clue about the pressure. We thought, okay, and we have our material, and we know the material properties, and what this slide just shows is that the temperature on which phase changes occur is dependent also on the stress conditions, on stress and strain. So if there was no mechanical stress and strain, in this case 760 degrees centigrade, change to austenite, And under real grinding conditions, you see this temperature drops down. So what is important, because at the bottom line, you would like to know the phases which you have in the material. So that has to be done by experiments. How can you do these experiments? So we made little specimens. You see a coil, ceramic punches, and then in between we have this material. We heat it up, put it under pressure, so we have pressure and heat, so according to the real grinding conditions, and then we send X-rays through that material. And according to the phases that we have, we see refractions of the X-ray, what is called Bragg's circles. So we see these patterns, and material scientists really can analyze what it is. So we have this correlation. How could we do that? You see this? That is really a high sophisticated test stand. So we met some friends in Hamburg. They have that are nuclear physicists. So they do particle collisions, and they look into so they really accelerate particles and they let them collide, and then they really look at the remains. And so what they did was, how they do that is they have a big ring, a tube with big magnets, and then they accelerate, for example, these particles. They let them collide, look at the remains. So they need time and they need space to do the acceleration. And the clever thing now was, let's make a circle, not straight away, then you need really kilometers. Let's make a circle and let's travel the particles in the circle. And there was a guy at MIT in the 70s, based on quantum mechanics. He said, okay, if you send nuclear particles in a circle because of the acceleration, they should emit radiation. And that's what they do. So the nuclear scientists were not happy about it, because radiation, they lose energy. So, well, in that case, they were not happy. But then the material scientists looked into this radiation, what is called synchrotron radiation. They looked into it and they found extremely bright, extreme high energy. And it really covers the whole span of electromagnetic waves. And if you just look at the visible part, it is 10,000 times brighter than sunlight is. So extreme high energy. The good thing now was material scientists came, okay, if that is the case, this sort of wasted energy for the nuclear scientists, we can use it. And they made filters, and now you have extreme high and powerful X-ray. And X-ray is good for material inspection. So we put all the stuff into these chambers where the nuclear scientists do their fundamental jobs. And we have now our things in there, and we use this sort of energy. And they were also happy about it, because they didn't know about grinding. So we came, what are you guys doing? Grinding, what is that? So we told them grinding is the most important thing in the world. Aside of this research, of course. Okay. So keep them happy. So meanwhile, we really build up a little machine. So in the next step, we really bring a whole machine into that chamber, that we really also can see under realistic condition what happens. So what do we learn there? Phase transformation. So, as we know that now, phase transformation, heat partition, could we model that? At least what you see here, we have an experiment and we have a simulation. So we cannot simulate distinct grains, but we can see the depth of the heat influence, and that very nicely matches. So if that was the case, now backwards, obviously our assumptions in the grinding were also not so bad. We were close, or we are close. We make it better. But we are on the way that we say, obviously it's proven so far that it could be a way to really predict also the surface properties of the ground material, of the ground material. So, and consequently also our assumptions in the grinding were not so bad. That's how we do it. Brings me to the last part of my talk, Industry 4.0. I just picked a few buzzwords. Now it becomes more global. Digital production. In Germany, we have this Industry 4.0, digital factory. That's what you also might hear. Industrialized Internet Initiative. Who knows that? Who doesn't know? You don't know? Brilliant factory. Who knows? What is a brilliant factory? So the Industrialized Internet Initiative that was born here in the US 5 years ago. 5 founding members. It was Cisco, it was IBM, it was AT&T, I don't know the others. So, and they came together, and the question is, they say, information and communication technology so have made a lot of progress in the past. Could we make this technology also available for factories? So we bring the new approaches of the Internet of Things, that is another buzzword, now to the companies, to the factories. And can factories make use of it? So that was the idea. So meanwhile, if you Google that, Industrialized Internet Initiative, you might find, I would say, 200 companies are membership, so they signed in, we also signed in this consortium, and they meet on a regular way, and they talk to one another, and they say, okay, sensors, for example, sensors in production technology, why not to use it? You do it in your company, and then they meet together, and then they report about their experiences. So that is a loose network on applying of the latest achievements in communication technologies. And the brilliant factory, that is a buzzword from GE. So GE says, okay, we do it. We are big enough. We are jumbo. And we call that a brilliant factory initiative. So that is more or less, that is the application of the things just to GE companies. Industry 4.0 is the same thing in Germany. So also the Germans, so we were not ahead, so we were a little bit hinten dran. What is hinten dran? we were slow. Okay. So we were slow. So 2 years ago, so there was, okay, we see there's something going on there. So we also need this initiative. So then the initiative was born, and now also we have this campaign in Germany just to look what the communication and information technology could do to make production technologies more efficient. And then we okay, so you know, Germans always like to standardize, yeah, okay. So at first we need a standard. So what we did then was in Aachen at least, you can talk now in this jungle, yeah, you can talk about everything, and then you don't have any track, any golden thread that goes through your talk. So we decided, okay, let's try to really make little blocks out of it, this Internet of Things. The one thing is this one here. So that is the shop floor where you run your machines, where your grinding machines are, where you make your gears. So, and that goes along also with sensors. That goes also along with automation. So that is one block you can look in. The second now is, I was talking about modeling, I was talking about sensing information, so it was also some sort of big data. 120 gigabytes, 1 week computing time to get 1 point. So obviously also we are dealing with big quantities of data. So that could be done here. So look into this area. What can we do on these platforms? How can computers help us to get better results out of our models? Could we also find new ways for new business models? Also a question. We'll touch that. So this one is the very beginning. So these where the engineers are, where they design the gearboxes, where you have your product lifecycle management systems. You start there. And your scheduling systems is also here. Okay, so that has also to be linked into this system, and then you have all this stuff here, what you already see. So we looked into it. So and why? So we just picked this slide. So what happens? Most likely you know that. Wait a minute. What happens in an internet minute over the years? You see this tremendous boosting of data which are available in these internet communities. And the only question was, can we make use of that also in the real making of products? Is it just for consumables? Is it just for the Amazons? Is it just for healthcare? Or is it also good for gear making? That was the simple question. Okay, so we asked people in industry, how do you feel about it? Have you heard about the internet? Yes, we have, because we all have our computer and we use these search machines. So asking the people in production, what do you think, how important is it for you? They say, okay, 1/3 say it's very important. The other say, another third says less important, and somewhat in between. They say important because most likely they don't know what it means. So some say very important, might be just for safety reasons, not to miss something, and the others really didn't hear about it. The second then is for the service. If you ask service people, which do maintenance, which really are the face to the customer, they have another sense for this stuff. They say, okay, that's really important. We have to communicate with our customers, etc. So for us, it's important. And then we try to bring all this information together, always again into this, you say, cluster, always 4. So managers can just accommodate 4 clusters, and that's the reason why we always take 4. So what you see here is, okay, the high technology is over there, so they really know what you are talking about. But the production guys are here, and they might be considered to be beginners, bloody beginners. The good thing is they have got a clue. And another good thing is, obviously, if you know there might be something in there, then you also move in the direction. So potential is high, and you really can get progress. So we set up a project where we really travel around the world, and we do interviews, different places in Europe, in the US, in Japan, and in China, also India, to ask people how they judge this new technology, and to see, well, at the bottom line, it is a global approach. Yeah? It is not a German approach, it's not an American approach, because production is also global. So it has to be realized around the world. And so that is our first output that we found. Okay, in Europe, the people think, okay, we are good engineers, but we don't make use these internet things so intensive. So the Americans, well, that's our daily life. What are you talking about? So that is, we do it. You talk about we do it. So the Chinese people just do cherry picking. So that's good, we do it. And okay, and the Japanese people are also very, very, let's say, open-minded. Say, okay, let's see what is going on there. So they are really mixed feelings. You know Fanuc company? Most likely you do. You know Fanuc company, this big controller company worldwide. Could you imagine that they don't have any access to the internet world? You cannot reach Fanuc by internet. They don't have internet. They say, that is Fanuc. If you go there, yeah, you see Mount Fuji, and everything is yellow because the color is yellow. So, yeah, but they don't have internet. They say, inside world. Internal, we do have internet, but externally, no. We have fax and we have mailboxes. Yeah, you send the postman, and then we communicate. And that is a world leading company. And why? They say because IP. Now we come to the IP, to the security of this data. So we really close it because IP is our value. Anyway, so we come back. That has to be solved. Data sources in manufacturing. Okay, it is gear grinding, of course, but also the machine can tell you a lot of things. And also your workpieces might tell you a lot of things. So you might combine that everything together, and then you really have big data. What for? Now you can really do on a professional way. You hire software engineers, not just mechanical engineers, but software engineers, and also mathematicians. And they do on a professional way data analysis and data mining. And they find out uncertainties, what is uncertain and what is statistics and what is a trend. What is a trend? And at the bottom line also might come up with new business ideas. So if that was not good enough, way back, rule-based models, also a good thing. So I just look at the very end. I just look at this interface between man and machine, because also in this new world, it is not a manless world. So people are still there. Might be they need to be educated in a different way. But in particular, our kids already, they grow up with iPads. So they work with their fingers this way. So they sweep. So they know that already. So the new generation most likely doesn't fear about it. The older generation has to learn about it. So I look a little bit in the man-machine interaction and to come up with some assistance systems, as we say, to help the people which run machines on the shop floor in decision making. And one thing, of course, is to set up apps. Now we do the same thing as you do if you download an app from Boston, Street Map. Now we can consider the same thing. So we run our processes in a cloud, why not? And you might also now get some information out of the cloud. You download apps to calculate cutting force components, to calculate heat partition, if the models are good enough. So to give you assistance. You also might have, let's say, smart interfaces which really directly communicate with your machine. So we have in Aachen many machines, and we have also these smart interfaces. And sometimes, so I have this smart interface in my hand, I go in the laboratory, and then I ask my machines, how do you feel today? And then they answer. So 6 which are just around, they say, okay, I'm under pressure today, I have to work hard. So that's what you see. Even if it is just power consumption, you could also see, for example, cutting force components. You could also see that something is wrong with the coolant supply or whatever it is. So this interaction with smart devices, with machines, and this particular writing of technology apps. It's a wide field for students. So they sit down and they write apps now for everything. And then you also get a library for these technology apps, so which helps you to take decision on the spot. And that brings me to the last few slides. Okay, a day at Perfect Gear Corporation. So we have this guy, he operates the machine, and he is satisfied, obviously. Okay, so good business. And a problem occurs, that's today. So what can he do? Okay, scratches his head, of course, number one, and then runs to his friend in quality department, asking, so what can I do? I have grinding burn. And his friend in the quality department, he is experienced, tells him, okay, go down with the feet. Yeah, that could solve your problem. It takes you longer, but you don't have any problem with the grinding burn. Okay, he says thank you, goes back, changes, and it is good. Okay, good production again. In the future, so by the way, this guy here, the abbreviation, okay, all right, okay, where does it come from? Does somebody know the story? At least I know a story where that came from. Okay.
All correct from German. All correct from the German.
Absolutely. Tell us the story.
I don't know the story behind it.
Okay. Well, the story is as follows. I don't know whether it's true or not. Yeah. In any case, it's a good story. So it was Henry Ford. He ran his production lines, and then he figured out an engine is the heart of each car, and he thought, okay, at the end of production, quality inspection. And to certify that everything was good, he assigned the foreman from the quality department to put his initials on any motor block which was proven to be good. So that's what he did. Hammer, initial, embossing. His name was Oskar Krause. He was a German. So okay. So that was the story. So he asked this guy, comes back, good. So next thing now, why not to use these apps? Yeah, that might be the future. Because his friend from the quality department might have retired. Yeah, mightn't be there. So then it's better you really have another source where you really can ask for and to go for it. And so that is really coming up. That is really new. That is very close to application. And well, it brings me to my last slide. ICT and organic technologies not work harder, but work more intelligently. That might be the conclusion. So, and if that was said, you can say, grinding wheel people always a step ahead. Thank you very much for your kind attention. I have one more slide. That was new business models, because I'm here in the United States, and you are always keen on new business models. This is that okay? A few minutes. So now consider we have this cloud, okay? And we send in information and we take out information. So as long as it is within the company, no problems with IP. So you keep it secure. So that's good. But now we thought, okay, we have machine tool providers, they provide the machines. We have tool providers, they provide the tooling. We have end users, so they use everything. They make gears, they make this and that. We have the raw material providers, they provide materials, also good, and other people. So we thought, could it be that you at least consider that you share your knowledge, that portion of your knowledge that you have is open to public. You share it. You are ready to share your knowledge with others. So first people really had to think about it, because of everything IP. What about our intellectual properties? But then they came to the point, yes, why not? We have already today, we have our internet pages. You can go there, you can see your grinding wheels on the internet, and you have catalogs, etc. You already provide knowledge to the outside world. Might be even a little bit more. Bring your knowledge where you'll be able to really put that knowledge on this platform. And we found 60 companies at least to try. So, okay, we try it. We make a try. We set up an environment, and then we try. We fiddle around. We play another toy. So on this, and they say, okay, we do it. And now we're really collecting information, which is where the companies say, different companies, different branches, different industries, but they say, okay, this sort of knowledge, we give it on the marketplace. And now we really receive a bunch of information in the cloud. Okay, and now if we puzzle together this information in different ways, we could make services out of it, different services. So the material provider, he really looks for another sort of service than the end user does. So now, at least, we have opened up a space where we could say, why not a new business model? Open question is, who owns this platform? Who is the owner? We don't have any answer for it for the moment. For the moment, just we say, okay, might be associations or whatever. But anyway, you see now collecting data on the one hand side, intellectual properties on the other side, it's one thing. The second thing is now share knowledge. And by sharing knowledge, to come up with new ideas in making new business, service business. So that is open, it's also on the way. And if we have some, let's say, good examples where that really works, that could also break the ice and could really open up new business models for the future. That was just an idea. Might be you think about it and you spin off your own company. In case you do, let me know. Thank you. Thank you so much. Welcome.
I want to thank Dr. Klocker very much for his wonderful talk, for the personal remarks on Steve. We're scheduled to go to 10:30, but we have to probably leave at 10:20, so we have time for 5-10 minutes of questions.
Go ahead. Yes, please.
Yeah, so getting this last point about sharing knowledge, you started it, I assume you've done this, and you're familiar with Tim Berners-Lee's semantic web vision, and
not so good.
well,
But help me.
that's the the semantic web is the web 2.0.
Oh, yeah, okay, yeah.
And the use of ontologies representing knowledge in ways that's shareable with people in software agents.
Mhm.
So when you're sort of looking at this business model and this interacting with your vendors and your suppliers, are you sort of formulating your knowledge in the form of formal ontologies so that when you expose it to them, that knowledge it's actually more intelligent software agents can reason on it?
Yeah, everything is open at that point in time. Really, everything is open for us because we don't have really a good way to do it in an organized manner, in an organized order. So we are just open for everything.
A lot of good ontology work has come out of Germany
Yeah, okay.
for knowledge representation.
Okay, good. Yes, please.
You started saying that Professor Malkin was look to the physics first,
Yeah.
understand the basics.
Absolutely.
Really, before you advance to this point, what's missing in the basics today that people who are doing research on?
Yeah, what is so well? Also saying this grinding wheel in front of the cutting edge, it's still dark. We cannot look at it, and that's the area where really the energy conversion happens. So as we look deeper into that interaction, as more we really learn about the processes. So we are still, with our models that we have, with our physical models, we are not close enough to the target. We have to do iterations, makes them better, and then they are just valid under certain boundary conditions. So okay, and that loses the general output. I think that is still going on. And the second, what we also really do not know is that is the prediction of functionality. I say it is this white layer. Okay, it's a white layer, but a gear has to perform, okay, under different conditions. Predict the functionality of a gear, we are far away from that. We just can say we wouldn't like to get a white layer, so what can we do to really get rid of white layers? But if there was something else, and whether or not that has influence on the functionality, we really cannot predict good enough. It is just experience-based. Last point on that, that is good. We have a research collaboration between Aachen, Bremen, and an American university, Don Luca, and we say, could we find, from the material point of view, as mentioned, a material doesn't care whether it's going to be ground or laser treated or whatever. The material just feels energy impact and energy conversion. So that's what the material feels, because nothing else. So could it be that we really could generalize the different impacts of different manufacturing processes on the surface of a material, that we say, if that was the same, if that was the same impact from different cutting processes, then we could substitute processes. Yeah. So if we could find that, if we could find tracks which are fingerprints for any process, and if these fingerprints look like the same, then we could substitute processes. That is an idea. So bottom line, why did we get the money? Because we could tell the story. We are not good enough in really predicting what happens on the material side. We are still far away from really knowing what happens in the material, predicting functionality.
Steve?
So
Yeah.
to follow up on that point, with the materials and the energy that can happen at that surface, instead of waiting to predict, has there been work done more proactively about different orientation of, say, the grinding agent versus the surface, the hardened zone of
Yeah.
the wheel? The different orientations of those grains, for example, orientations of that, the energy would be much more predictable.
Yeah.
You can texture the
Yeah.
surfaces of either one.
Oh,
Has
yeah.
that been done?
Yeah, absolutely. Yeah, that's also under observation and under work to really have, if I understood right, you say you could do patterns in a certain way, structures on a surface of a grinding wheel, and then you really more precisely analyze the energy conversation. Is that what you mean?
Partly. Even with the cutting edges, for
Yeah,
example,
yeah.
each of those individual grains,
Yeah.
if there was a preferred orientation, or if the hardened
Absolutely.
zone,
Yeah,
hardened zone of the gear wheel should have grains that, when you show the synchrotron radiation, you have these polycrystalline
Yeah.
rings.
Yeah.
So if there was, some random distribution, you'll have an averaging effect. Whereas if you actually,
Yeah, good
texture
thing.
the grains, you actually be able to predict the energy.
Yeah. So, well, the grinding wheel makers might punish me because if I'm now talking about patterns on grinding wheels, so that really might be pain in your neck then to really make these wheels, to really set them according to different patterns. But we really did it for research, really to get rid a little bit of this random effect. In any case, a grid is a grid, and there's also variation from one grid to another one. But then we don't have this random distribution, then we have distinct patterns, and then we can better study. That is correct, and that's what we really do. But by the way, in rollers, in diamond rollers, you might still have this. You have handset diamond rollers still, yeah. Some of them too expensive, aren't they? Yeah.
Oscar. What was his name?
Are you from Norton?
Yes, Pennsylvania.
Or Saint-Germain? The largest diamond roller we made in Hamburg was for Caterpillar. So they made these Caterpillar things. That was a handset diamond roller, yeah. I still remember the numbers. It was 400,000 single diamonds. 400,000. So this size, this long, this diameter. So it was reverse plated. And who could set the diamonds? Only women. So we did have women, and they really picked the diamonds hand by hand. There was a glue, so you made a reverse profile, and they picked them according to a pattern. Because in that particular way, it was necessary because there was a big difference between the diameters. There was a large diameter, a small diameter. And then you really also had to change the distance of the diamonds to get a surface topography of the wheel, which at the end didn't burn, yeah. It was 200,000, but you couldn't really pay it. So it was really, we never...
Oscar Krause's children, I guess, you hired.
I tell you one thing. So I don't know whether that is still the case. So it was just, we did have many women, they really did have the ability, and that was the other way around. So, well, they had a mirror. They looked inside, they picked it here, and then they placed them this way. And after half an hour, they really had to reset their eyes. It was so extreme, yeah. Then they stopped, and they went into another room where we did have just leaves, yeah, and they looked into the leaves, and there was some noise, and then everything was reset, and then they started again.
All right. One more question, sure.
Yeah.
Just a follow-up question about this idea of using, studying a single grit to understand the
Yeah.
partitioning and what's happening in grinding. I was wondering, so you mentioned the use of high-speed imaging. I was wondering how you use that to model this energy partitioning.
How we use it?
To develop models like the high-speed imaging. Is it infrared or is it just optical?
That was just optical. It was just optical, and it was a force component. So we
Yes.
measured the cutting force component,
Okay.
and it was optical.
Okay. So there must be some, I don't know what model you're using though, so you have forces?
And we have forces, we have the engagement conditions.
Yes.
We have forces, we have engagement conditions. We make assumptions that all the heat is going to penetrate into the workpiece, or that let's say 50% goes into the grain or whatever. And with these assumptions, we came to energy partitions.
Okay.
Which
Do you
go
use
into
thermocouples or anything to try to verify the
Yeah, yeah, as mentioned that way. So then that was one idea. So we say, okay, under these conditions, 60% goes into the workpiece.
Okay.
So if that was true or not was verified at the bottom line just by doing microscopic investigations on the workpiece.
Okay. Understand. Thank you.
Mhm.
All right, I want to thank everyone for attending, thank Ruth and Matthew for coming here, thank all the St. Gobain employees. We will be going over St. Gobain, in fact, if you're interested, we'll be going over with Dr. Klaka to Kellogg. If you wait, then I'll guide you over to the next meeting place, okay? Thank you very, very much.